Okay, so we're looking at the second video from 8.2, and this one's just going into a little more detail in discussing indeterminate forms, what they mean, why they are, and things like that. We're actually going to talk about why some forms are indeterminate and other forms are not, and how to recognize those. So what makes an expression indeterminate? Well, consider the situation that we know is indeterminate, infinity over infinity. So if we can hold one part of the expression constant, for instance, if we take the limit as x approaches infinity of x over 1,000, so we're holding the bottom as constant, this thing's going to go off to infinity. Now if we turn around and we flip this and we let the top stay constant but the bottom is varying and x goes to infinity, then we end up with 0. So this should kind of give you an idea. If one of these is growing faster than the other one, then that's going to give us different answers. That's why this is an indeterminate form, because unless you know the top or the bottom, which one's growing the fastest as x goes to infinity, you can't identify if you're going to infinity or if you're going to 0. That's why we call it an indeterminate form. So we have two different trends, one going off to infinity if we hold the denominator to be growing slower than the top, and this one over here going to 0 if the top is growing slower than the bottom. The actual limit will depend on the rates at which the numerator and denominator approach infinity, so we say that an expression in this form is indeterminate. So unless we know more information, we can't do anything about it. That's where we can use L'Hopital's rule on our limit and go from there. Because remember, what is a derivative? If you take the derivative of the top and the derivative of the bottom, you're just finding what? The rate of change on the top versus the rate of change on the bottom. So you're comparing their rates of change. All right, let's look at another one. Consider infinity to the 0 power. And let's look at what happens. Well, if we hold one part of the expression constant, like for instance here, we're going to hold the base constant. It's going to be a really big number, but we're going to let the variable, or the exponent, approach 0. So 1,000 to the 0 power is just 1. 1 million to the 0 power is just 1. 1 trillion to the 0 power is just 1. So even if the base is still growing, if the exponent's growing at a faster rate, it's going to approach 0 much faster than this is going to go to infinity, so we're going to end up with 1. What happens if we flip it around? We let our variable, our exponent, be some small number, but we're going to let our base vary and go to infinity. Well, infinity to the 0.1 power is still going to be infinity. So that in that case, we know that we've got 1 here, we got infinity here. Well, what about if we're approaching from the negative side? Let's say our exponents are negative. Well, it's going to approach 0 then, because remember the negative is going to flip to the bottom, so it's going to be 1 over x to the 0.1, and x is still going to infinity, so the denominator is getting larger and larger and larger and larger, so we go to 0. So here, with this case, depending on what we're holding as constant or letting grow at a slower rate, we're going to approach different values, very, very different values as a matter of fact. So due to these conflicting trends, we know that this form is indeterminate. So we have to do other analyzation. Most likely L'Hopital's rule, and you're going to have to use an E in natural log to be able to bring this thing down, this power down in front of the natural log, and then deal with it there. All right, now finally, here's an expression that might look, or that looks like it might be indeterminate. 0 to the infinity power. All right, so if we hold one part of the expression constant, for instance in this first one we're going to hold the base constant, and we're going to let the x go to infinity. So we're taking a really small number, 0.1, it could be even smaller, but if you do that, you're multiplying a fraction times a fraction multiple times. Well, think about what happens when you do 1/2 times 1/2 times 1/2 times 1/2 times 1/2. You get one, I think I did 4 of those. If I did 4, it would be 1/16. If I did 5, it would be 1/32. But what happens is the larger that power gets, what do we notice about the fraction? The fraction is going to get smaller and smaller and smaller and approach 0. So as we take some really tiny number and multiply it by itself a lot of times, this thing's going to get smaller and smaller and smaller and go to 0. All right, now what happens if we do a negative? Well, it's still going to approach 0, because a negative one is still going to approach 0 for the same reason. It's just going to approach it from the left side. So it's still going to approach 0, it's just coming in from the left. All right, and then what about if we let the base go to 0 and we let x be a really large number? So here, if we let x equal 0, 0 to the 1,000 power is still going to be 0. So here we know that we've got 0 here, 0 here, and 0 here. So where we know that infinity to the 0 power is indeterminate, since all of our situations here give us the exact same number, this is not an indeterminate form. 0 to the infinity is not indeterminate. So you've got to be careful and make sure that what you're dealing with isn't an indeterminate form. All combinations of 0 and infinity are not, like the case right here. So in this case, the limit of this thing is 0 any way you look at it. Whichever way one you're holding constant or small, and the expression therefore is not indeterminate. All right, now here is the standard list of indeterminate forms. These are all the ones that you're probably going to see in your math career until you get into the really high maths if you take those. 0 over 0, old standard. Infinity over infinity. These are the two that we can easily use L'Hopital's rule with. And then we get the ones that we're going to have to do some work on to get it to be a L'Hopital problem. Infinity times 0. Infinity minus infinity. When you're doing a subtraction or an addition or anything like that, you got to remember that you've got to get a common denominator and you've got to get them together, because you're trying to get them in this form right here or this form right here. If you can get them in one of these two forms, L'Hopital's rule works. You can't just do L'Hopital on infinity minus infinity. You've got to change it to get it into one of these two forms. You can't just do L'Hopital's rule on infinity times 0. You've got to get it in one of these two forms. It's got to be a fraction. It's got to be a rational expression, one polynomial or expression over another, before you can use L'Hopital. Right? 1 to the infinity is also indeterminate. And 0 to the 0 power is indeterminate. Where 0 to the infinity power was not, 0 to the 0 power is. So make sure you notice and remember the difference between those two. And then infinity times 0, the one that we started off with talking about, or one of the ones we started talking about, is the last one that's going to be on your standard list that you need to definitely recognize. Now, there are other indeterminate forms using complex numbers, but those are way beyond what we're going to talk about in this class. So you don't have to worry about any of those, but these you should be able to recognize and kind of get an idea of how to swap them over. Remember, you're taking them back into one of these two forms right here. You need to be able to take these and put them in that form. All of them are going to be, all the ones with powers, of course, you're going to use the e and natural log. This one, of course, you're just going to do the reciprocal of 1. Whatever is going to infinity, you're going to divide by its reciprocal. Then it's going to be 0 over 0. And then this one, you just have to find a way to get like common denominators and combine them together into one fraction and see what you get from there. So that's how you deal with all these. All right, that is all of this little short segment. So definitely look at these and think about how you could change them over into the two methods that we can use L'Hopital for, or the two forms we can use L'Hopital on.